This is going to be the lecture over chapter 30. This is going to be section 30.1. We're going to be looking at properties of nuclei. So an atomic nucleus is roughly spherical with a radius that increases with the number of nucleons in the nucleus with this particular relationship. This is going to be your starting radius, and then as your number of nucleons, which is represented with the letter A, grows, then you take basically take that to the 1/3 power, or take the cubic root, and that's going to give you your new radius. So the total mass of a nucleus is always less than the total mass of its constituent parts, because the mass equivalent of the binding energy holds the nucleus together. What that's essentially saying is that if you were to take all of the components of the nucleus of an atom and you were to take them out and just string them along individually, they're going to have certain masses. When you push them all together, you're going to end up with less mass than what you had before. And the reasoning for that is that you have a certain amount of energy that it's going to require in order to hold that sucker together. And so that mass defect that you have there, the difference between what the nucleus actually weighs and all of its constituent parts, that goes to energy to hold it together. So as you can see here, or at least as soon as I scroll up to the top, that nuclei are going to be composed of protons and neutrons, and that is a proton or a neutron collectively together is going to be referred to as a nucleon. These two particles have nearly equal masses. They're pretty close. It's not exactly equal, but you're looking there at 1.67 times 10 to the minus 27 kilograms, very small. They're not fundamental particles, but they're composed of more basic entities called quarks. The total number of protons in the nucleus is going to be represented with the atomic number, and it's going to be labeled as Z. In an electrically neutral atom, this is going to be equal to the number of electrons. Hence, Z determines the chemical properties of each element. The number of neutrons, denoted by N, is called the neutron number. And the total number of protons and neutrons, when you add the two together, you end up with the nucleon number, and it's denoted by A. So the nucleus is 20,000 to 200,000 times smaller than the atom itself. So you can picture it roughly as spherical, although you've seen before the pictures of it. It's not exactly spherical, but that's how a lot of people look at it because it's just easier to think of it that way. The radius is going to depend on the mass, which in turn depends on primarily on the total number of nucleons. The radii of most nuclei are represented fairly well by an empirical equation. In other words, it just works. This empirical constant here, 1.2 femtometers, that's just sort of your basic constant, or you can think of it almost as a base radius in a sense. So you can see here, since volume is proportional to the radius cubed, then having a cubic root here for the number of nucleons is not that surprising. It also follows that the density is the same for all nuclei. In other words, all nuclei have approximately the same density. Since they're about the same mass, this doesn't come as too much of a surprise. So a single nuclear species that has specific values of Z and N is called a nuclide. You can see here the list of values of A, Z, and N for some nuclides. For an atomic electron structure, and that's going to determine chemical properties, is determined by the charge Z times E of the nucleus. The table shows some nuclei with the same Z but different N. When you have a situation like that, it's called an isotope. Iso meaning the same, and tope here, since it's got the P in it, means the protons. In other words, same number of protons. So in other words, you can have a chlorine atom which has a Z of 17. You're looking at about 3/4 of chlorine having 18 neutrons. The other 24 has about 20. Because of the differing nuclear masses, different isotopes of an element have slightly different physical properties. Melting point, boiling temperatures, diffusion rates, things of that sort. For uranium, you've got a nucleon number of 235 and 238, and those are separated industrially for use in atomic weapons and commercial nuclear power plants. The separation is achieved by means of centrifuge or by taking the advantage of the different diffusion rates of gaseous uranium hexafluoride. So it's more complicated than that, but that you get the gist of it. So in the same table you see here, you've got the symbol of the element, you've got the pre-subscript equal to the atomic number, and a pre-superscript equal to the mass number. In other words, A is let's take a uranium here, uranium 238. The 238 is going to be A. The number down below it on the left is going to be Z. If you saw a number over here, it would tell you the number of neutrons, which would be A minus, or A minus Z. Specific masses of protons and neutrons are listed here. You can see that they're the same up until the third decimal place, and then things start to differ a little bit. So since the values are nearly equal, it's not surprising that many nuclear masses are approximately integer multiples of the proton or neutron mass. For precise measurements, it's useful to define a new mass unit equal to 1/12 of the mass of a neutral carbon atom, with a mass number of A is equal to 12, and that is defined as an atomic mass unit. In unified atomic mass units, the mass of the proton, neutron, electron are all listed here. These values are more precise than the U2 mass unit to kilogram conversion factor, because atomic masses can be compared with each other with greater precision than can be compared to the standard kilogram. And 1 mole of the particles with mass of 1 atomic mass unit each would have a total mass of exactly 1 gram. You can find the energy equivalent by taking the value here, which is the same value up here, multiplying it by the speed of light squared, and that gives you the amount of energy. The masses of some common atoms, including their electrons, are shown here. Some tables always give masses of neutral atoms rather than masses of bare nuclei. In other words, atoms with the electrons stripped off, because it's much more difficult to measure masses of bare nuclei with high precision. So to obtain the mass of a bare nuclei, subtract Z times the electron mass for the atomic units. So the total mass of a nucleus is always less than the total mass of its constituent parts, because of the mass equivalent of the internal kinetic energy and of the negative potential energy associated with attractive forces that hold the nucleons together, holds the nucleus together. This is going to be called the mass defect, and it's denoted by delta M. The magnitude of the total potential energy is called the binding energy, and so the binding energy is basically going to be the mass defect times the speed of light squared. And the mass defect for a nucleus with mass M containing Z protons and N neutrons is going to be this. M is going to be the mass of the nucleus, which is always less than the sum of the masses of the individual protons and neutrons. So you can see some exercises that go along with that. It's really not too difficult of an issue as far as going through all of those computations. It's really not too bad. As we've discussed, the orbital and spin angular momentum of electrons and atoms, the proton and neutron are also spin 1/2 particles. Each has a spin angular momentum that has a component of plus or minus 1/2 h bar over 2 in any given axis direction. And in addition, each particle can have an orbital angular momentum due to the motion within the nucleus, with possible components in a given axis direction that are integer multiples of h bar. The total angular momentum of a nucleus is usually called nuclear spin, although in general it's associated with both orbital and spin angular momenta of the protons and neutrons.